Sir, are you there?
Yes, I'm here.
Okay. So now we reach the final session for today, where we have the privilege of delving into the captivating world of electronics and electrical communication skills. This field combines electronics, electrical engineering, and communication systems to develop advanced technologies that power our modern world. Joining us today to share their valuable insights and expertise in this field is the esteemed Professor Bratin Ghosh from IIT Kharagpur. Professor Ghosh is engaged in leading-edge research on Green's function-based computational techniques, efficient antenna design and analysis, miniaturized antennas, and metamaterials. Additionally, he serves as an invited speaker, a member of technical program committees, and session chair at various national and international conferences. He also contributes to the review boards of prominent national and international journals in microwave engineering. I now request him to address the curious minds in our audience.
Good afternoon. Am I audible?
Yes, sir.
Okay. Good afternoon to everybody. It is quite good. It feels quite nice, and it is a good privilege that you have given me the opportunity to share my thoughts on the topic or the subject of electronics. Now, this discipline of electronics in different IITs, like in IIT Kharagpur, is taught as a different discipline, as a separate department, while in some other IITs, it is taught in the general branch of electrical engineering. And such is the system also in most of the parts of the world, where the subject of electronics is taught as a subset of the mother branch of electrical engineering. Now, so if I look into this particular topic of electronics, the advent of this particular branch of study rose with began with what we begin in our study as diodes or transistors in our grade 11, grade 12, or PN junctions. Okay, so basically the significant boost towards research in this direction came from as in most other branches of engineering as well, the Second World War. Okay, so where essentially we had to cater to the needs of remote communication. Okay, so the remote communication is a very important feature, how you win a battle or how you cause destruction. So in that sense, the beginning of electronics is not that, in that sense, was not that beneficial to the human race. But what began as something designed to, to kill millions or to destroy cities or to win over battles and to engage in high-tech techniques to win wars, later came to be something which was used in a very different domain, which we are all aware now. But what is this journey? How did this journey take place? If you have to look at this journey, you have to look at history in its conception or in its inception from the Second World War to what we are now today. So particularly with the war or the Cold War between the two superpowers who emerged as the sort of the leaders after the Second World War, the Russia and the USA. Okay, so we struggled towards who would reach the moon first, who would conquer space first. And there again, the world of electronics or the world of remote communication, okay, the world of wireless communication got a heavy boost, because you cannot have an airborne vehicle without, wireless communication. In fact, if you talk to any scientist in ISRO or any scientist in NASA, he will tell you, or he or she will tell you, that one of the most significant components is the antenna. okay, which is the antenna is lost. So everything in the mission is lost because you lose all communication between the spacecraft or the airborne vehicle to the ground. So you lose the entire mission. So, and it has happened in the past. So one be very careful of this kind of communication link. Therefore, different types of antennas are employed to serve different purposes. Even if you look at a civilian aircraft, okay, it has numerous antennas on board, each serving a different purpose. Okay, there are antennas which are measuring the height of the aircraft from the ground. There are antennas which will guide the aircraft through, like to inclement weather, through weather where nothing can be visually seen. Like, for example, in a snow-clad terrain where an airplane has to land, okay, where with zero visibility. And this happens all the time in our country, in different countries of the world, where aircrafts have to land in different scenarios. So, therefore, how you communicate, okay, this with or without a guided structure or without a wire is one of the very important areas of research in electronics. So broadly, the electronics is divided into a number of specializations. One is the low frequency electronics, which is we call it the VLSI, the very large scale integration techniques, VLSI circuits, VLSI systems. Example, the systems which are used in the motherboard of processors, like the PCs or your circuits which are used in low frequency, in your mobile phone, everywhere. Okay. Then we have circuits which are used at high frequencies, which are now the advent of high frequency is the beginning of what we call the microwave technology. Okay, so in the microwave technology, we design circuits which begin from typically a few, like maybe it's 700 megahertz, 800 megahertz, typically 3 gigahertz and above, but it can range to 94 gigahertz, 100 gigahertz or beyond. Okay, but typically the microwave frequency range is from 3 to 30 gigahertz. Now we have the millimeter wave technology, which is the high frequency range above 30 gigahertz. And like above that is we have the light wave technology or the fiber optic technology that is taken care of by a different specialization, the fiber optic and light wave engineering. Other than that, we have the telecommunication system engineering, okay, and the VIPes specialization, the visual information and signal processing. Now, essentially, the majority of the electronics will deal with the hardware systems, the circuits used to design, like communications receivers or transmitting systems, and do processing of the signals. And the other part of the electronics will deal with essentially the software part, speech processing or like signal processing, those kinds of areas which happen after the signal is converted to the baseband. And what is this baseband and what is this high frequency? Basically, if you look at the architecture of the super heterodyne receiver, okay, that is the quote unquote the kind of systems which we are dealing with electronics. So at the front end sits the antenna. The antenna is supposed to receive signals from outer space when it is receiving, and it is supposed to transmit signals when it is transmitting. And there are many components in the super heterodyne system, but roughly then you have the low noise amplifier, and to clean the signal up when the antenna is in the receiving mode. And then you have what we call a mixer. So the mixer converts the signal at high frequency to the low frequency. Why this is done? This is done because if we consider the transmitting system, we cannot transmit the low frequencies due to a variety of reasons. And one of the prominent being, we would need a very large antenna to transmit a low frequency. So in order to have the antenna length within reasonable limits, okay, because the antenna length is roughly given by, for a dipole, it is roughly given by lambda 0 by 2, the free space wavelength by 2. So the antenna length has to be within reasonable limits means the lambda 0 has to be within reasonable limits. So therefore, your frequency has to be upscaled or up converted to such a level such that lambda 0 is reasonably small, so that the antenna length is reasonably small. So the antenna is supposed to, as I said, that is, it is supposed to radiate signals for the transmitting case and receive signals for the receiving case. But what demarcates the low frequency and the high frequency? We all know that what we read or what we do at low frequencies has to do with the analysis of low frequency circuits that is based on familiar laws like Ohm's law or Kirchhoff's laws. We are all aware of things like Kirchhoff's current law, Kirchhoff's voltage law, and things like that, with which we analyze low frequency circuits. However, we cannot use the same concept for analyzing high frequency circuits. When components in the system become comparable to the size of a wavelength, we cannot use Kirchhoff's law or Ohm's law to predict the current or voltage in a circuit component. In fact, the concept of current and voltage does not exist at all. If the concept of current and voltage does not exist at all, what exists? We talk about what we call electric and magnetic fields. So those are the bedrock of what we can call the measurable quantities of the observables we can measure at high frequencies. And how are these measurable quantities linked? They are linked by a famous set of equations called the Maxwell's equations. So what we study at low frequency in grade 11, grade 12, and even when we deal with static electricity, in fact, when we deal with static electricity, we first of all encounter the concept of action at a distance. That two charged particles, okay, located, separated by distance, would either repel or attract each other. And Coulomb's law gives the expression through which we can calculate such attractive or repulsive forces. Okay, but come to the moving charge. If the charge starts moving, okay, as in a current carrying conductor, then we have magnetic fields. And then we have concepts like Ampere's law, which will give you the magnitude of the magnetic field for a steady current carrying conductor. We have read Ampere's law in our grade 11, 12. Okay, but then specializing from that, or rather broadening from that, we come to the generalized Maxwell's equations, which will predict everything, including transmission and radiation at high frequencies. And high frequency, working at high frequency is one of the very important components in electromagnetics, because in electrical or electronics and communication, because without working at high frequencies, this word communication will not exist at all. You cannot communicate without using, like the concepts at high frequencies, or without using the concept of microwaves, or without using Maxwell's equations. Okay, so this world of communication, the hardware of communication, in fact, what we see on the right hand side of the mixer, okay, from the antenna to the mixer, okay, will be dominated by microwave components. And what we mean dominated by microwave components, you have two sets of components. Basically, the world of microwaves is divided into two. One is the systems which transmit the electromagnetic wave, or the so-called the system of electric and magnetic fields. And the other is what we already talked, which is the antenna, which radiates the electric and magnetic fields. So the first structure which transmits electromagnetic energy from one point to the other through a guided medium, okay, this system is called waveguides or guided structures. And the other kind of structures which radiates this wave, okay, is radiating structures, which are antennas. So what can be that, the best place to study the desirable characteristics of guided structures, what is desired of antenna structures, is very important towards understanding where we are going in future. Wherever we are going now in the future, whether it is 5G communication or beyond, depends on more and more improved hardware systems. There is no concept of building efficient software algorithms, which are extremely needed. But without a parallel hardware backbone, okay, there is not much use in contemplating what would happen if I would migrate to higher frequencies. We have to build the hardware backbone. And electronics considers itself distinct from other branches of electrical engineering, particularly in building the hardware backbone for communications. In addition to the software needed, the design of efficient software, the design of efficient algorithms, okay, needed in communication and needed in the processing of signals. So everything which is related to the communication area, particularly the hardware and the associated software, is under the direct under the direct supervision or under the direct area of study of electronics. So you can appreciate that it is a very vast area which caters to a very important thing, because without communication today, without internet today, without efficient algorithms today, it is worse than, if not otherwise, it's worse than living without power. You are forced to live in the Stone Age. If I take out your mobile, you are nowhere. If I take out your internet, you are nowhere. So it is important to understand how these efficient systems work and where we are going. So first of all, how these efficient systems work? What is needed? It is needed to design faster and faster systems which use lesser and lesser power at lower and lower costs. So everything is very good. Your system is faster. Your price is falling, and you consume less power. Though it is said in three simple words, to achieve this is very, very difficult. Okay, because as devices get smaller, they become less efficient. If you take, for example, an antenna, I just now told you that a dipole antenna is of length lambda 0/2. Now somebody can say, I do not have space to give you a lambda 0/2 antenna. I do not have space. So what do? I have space for a lambda 0/10 antenna. But the lambda 0/10 antenna won't do, because the lambda 0/10 antenna would be very less efficient. So one of the researches these days is to how to make sub-wavelength structures work, how to miniaturize devices, how to miniaturize components, and number one, miniaturize components keeping their efficiency. Now, when I talk about this kind of miniaturization, we have to understand a little bit deeper into what we understand by high frequency communication. Unlike, as I said, low frequency, the Ohm's and Kirchhoff's laws, the world of Ohm's and Kirchhoff's at low frequencies, at high frequencies, you employ what we call the transmission line concept, because you apply essentially KCL and KVL in an incremental length of wire. And as you develop the subject, you come across the modes, which are solutions to Maxwell's equations under a given boundary condition. For example, if I want to communicate electromagnetic wave from point 1 to point 2, I might devise of a rectangular structure which is bounded on all sides by conducting wall. This is called a rectangular waveguide. And inside the rectangular waveguide, we do not talk of voltages and currents. We talk of modes in a rectangular waveguide, much akin to the modes of a stretched string. But those are mechanical vibrations of a string. Here, we are talking of vibrations of the electric and magnetic field. In fact, here it is very relevant to say that light is also an electromagnetic wave, and it propagates by vibrations, orthogonal vibrations of the electric and magnetic field. So when we confine such electromagnetic fields inside a structure in order to communicate it, in order to transmit it from one place to the other, we have to understand the modes in such a structure, because that is achieved by distinct modes of the guided wave structure. And we have to therefore understand what makes a guided wave structure efficient. In order to understand what makes a guided wave structure efficient, we have to understand what causes inefficiency in a guided structure. The most important source of inefficiency in a guided structure, one of the most important things is the conductor loss. As you surround the rectangular waveguide, or design the rectangular waveguide with 4 walls on all sides and propagate the electromagnetic wave, currents will be induced on the surface of the waveguide, which will heat up the waveguide walls. Now, the important thing to realize is that as you move up and upper in frequency, or higher and higher in frequency, such conductor loss is going to increase to a phenomenal extent and will prohibit and will limit the efficiency of such structures. In order to do away with such kind of a topology, many kinds of structures have been proposed, many kinds of hardware have been proposed. How to cater to the needs of higher frequencies? If the conductor loss in a rectangular waveguide is a severe limitation, what to do? There had been different attempts, there had been some failures, there had been some successes, and research is always going on. For instance, in one attempt to minimize the loss in a rectangular waveguide, we can ask ourselves a question: can we restrict the number of metallic plates in a rectangular waveguide? Can we have 2 metallic plates like that and have a dielectric strip in between the 2 plates that will guide the wave? So I have 2 metallic plates like that and have a strip of dielectric in between them in order to guide the wave. What will happen? In such a case, the dielectric will enable the wave transmission. In fact, as the permittivity of the dielectric will increase, we will have better confinement of the electromagnetic field. But everything in engineering comes at a cost. Particularly at the higher the frequency, the more the number of parameters. And what is this number of parameters? As you attempt to reduce the number of metallic walls, there will be radiation from the sides of the waveguide. So we are going to encounter radiation loss from the sides of the waveguide. So in our attempt to reduce conductor loss, we will invite radiation loss. So there has to be a delicate balance between the two. You cannot have the best of both worlds. So we have to have a delicate balance between the two as to how to minimize conductor loss and yet minimize radiation loss to as much extent as possible. Such structures have been invented. Okay? There are efficient guides which are very efficient, I should say, both from a radiation perspective and from a conductor loss perspective. But then again comes the question of frequency use. When we began this world of communication, it was initially limited to the military and the space. When we fought the days of the Cold War, when we vied with each other as to who would land on the moon first, it was the military of the space who knew about microwaves. We, the ordinary people, the person on the street doesn't have any idea of what a microwave is. The research groups at the universities, the militaries, and the space who are actively working in that field know about microwave. So they have the lavish use of what we call spectrum. This word spectrum means that you assign a particular frequency to some application. Because the number of applications are few, so we could be more lavish users of spectrum. But when microwaves infiltrated the lives of the common man, when the internet revolution began, when the common man started understanding what microwaves can do to them, and now almost so deep in it, such that we cannot contemplate without any internet connectivity, or we cannot contemplate anything without wireless connectivity. So now the emphasis of research is very, very different because there are a lot of users. So therefore, if I have to allocate frequency ranges to a lot of users, that means our lower frequencies will be jammed up, they will be used up. So that will force us to go to the higher and higher frequencies. Not only that, what we contemplated as a single antenna, our antenna working at a single frequency, might be very lavish now, because we would now like devices which have reconfigurability. A single antenna doing different kinds of jobs at different frequencies. At one frequency, it can be a circularly polarized antenna. At another frequency, it can be a linearly polarized antenna. Okay, so, or like multiband and broadband antennas and miniaturized multiband broadband antennas. So therefore, multifunctionality and miniaturization make the all electronic component design much more complex. You have to also think about the heat dissipation aspect. How much heat the component is dissipating. In fact, that research is as important as the electronic part of the design. Because if the heat is not drained out effectively, your device is going to burn out. You might satisfy the electromagnetic principles or Ohm's and Kirchhoff's laws, but your device may be unstable from the point of view of heat dissipation. So that is as important as the electronic or the circuit design aspect. Okay, so therefore the miniaturization part, the low power dissipation part, as the devices are getting miniaturized, you have to also make it within the reach of the common man. So in the respect of antenna design, because the antenna is the most real estate hungry component on the motherboard. It occupies the most space in a motherboard. So if you reduce the antenna size, or if you can successfully reduce it, succeed to reduce it, you would save a lot of space on the motherboard. So therefore, if you think of that, there are a lot of issues there. Immediately, the bandwidth is going to reduce. Immediately, the efficiency is going to fall down. Okay, so this brings us to another important concept, the bandwidth. We now want to deal with big data. You will hear all the, like the people who are working in different other branches of engineering talking about big data analysis. We want to process huge amounts of data. Okay, that is everywhere. Okay, nowadays we have to search a lot of data. We have to take in AI, in machine learning. We have to scan through a huge amount of data. And that means huge amount of data transmission. And huge amount of data transmission at a faster rate, which is synonymous to having a large bandwidth. From a hardware perspective, we need very broadband systems. Systems which are very, very reliable. Reliable means that, for instance, you want to transmit from the Earth to the satellite. So you want to achieve a kind of signal which is not only polarized in one direction, like not only linearly polarized. Because if you have a signal which is linearly polarized, that is the electric field is only pointing in one direction, there can be an obstacle or there can be an environment which the signal meets, which will dampen that kind of polarization, which will be sensitive to that polarization. So we have to have a communication mechanism which is immune, which will be rather relatively immune to the diversity of the terrain or the diversity of the environment through which the signal passes. And also to cater to an arbitrarily oriented receiver. Because if my signal is linearly polarized, the receiver has also to detect that particular polarization. If the receiver is misaligned, it will not detect that polarization. So therefore, to allow flexibility of receiver orientation, it is very desired that we have signals which are circularly polarized. So to incorporate circular polarization in this, the moment we incorporate other features into the communication, the design becomes much more challenging. Okay, so in essence, we employ different kind of circuit skills. We employ different kinds of design of waveguides. We employ different kinds of antenna design. There are antennas which are looking at distant galaxies, radio astronomy antennas, which are looking at distant stars. Okay, so they are huge antennas. They have typically very high directivity. That is, the beam is very sharp. We have other kinds of antennas which must be low profile. That is, they must be restricted in a smaller environment. So if the antenna size becomes electrically small, their directivity is going to fall. That is, they are going to radiate more omnidirectionally. But we might want both. We might want a system which radiates, which has a relatively higher directivity, but also occupies a smaller space. So these are two conflicting requirements because we cannot give space. Space is at a premium in this world now. We have millions of devices, so each device must have smaller and smaller space. So we need to cater to different engineering requirements, engineering concepts, engineering needs in a smaller space. As we are entering the internet revolution, okay, we have basically started the internet revolution. In 1990s, we didn't know nothing about the internet. The common people doesn't hear anything about the mobile. Okay, so within how many years? 30 years, we are almost as dependent on the mobile as dependent on any other electrical gadget. So imagine 30 years from now, or by the turn of this century, in our lifetimes, okay, or in many of your lifetimes, you will observe the internet revolution, the electronic revolution grow in leaps and bounds. There is no limit to what is coming. Okay, the only thing is sustainability. We have to sustain our development. Environmentally, we have to be friendly. So those are very other areas of research. How to make our, our development environmentally viable. So there are a lot of things to communicate. There are a lot of in-depth issues, but unfortunately, we cannot go inside that without having a basic knowledge in this field. But the idea behind this presentation is to give you, or the idea behind this talk is to give you the enormous opportunities for this branch of engineering. It is the the electrical engineering is the biggest branch of engineering, and out of that, electronics is the most the leading branch of engineering in that field. So there are vast opportunities, there are vast areas for development, and we have just begun. Okay, it appears that we have progressed a lot. Yes, we have progressed since the Second World War in 1939 to 1945. We have progressed a lot. Definitely, we have progressed a lot. Needless to say, but I would say that it is just begun. Okay, so we have a lot to do, and you are going to see the results as it comes. And the most important thing is that how to devise more and more efficient devices. Okay, nowadays, the world of electronics, the hardware of electronics has to do a lot in advances in material science. We need different kinds of materials or novel materials which we cannot mine out of a mine, which we cannot get from a mine. For example, things like metamaterials, metasurfaces, okay, engineered materials, single negative materials, double negative materials, okay, and each of them are designed to overcome the barriers which existed while we used traditional materials. Again, research on this has just begun. Okay, so we have already contemplated many of such devices which actually go much beyond our imagination. Okay, we have conceived devices which are very, very small and yet can resonate. Resonances in sub-wavelength structures is an extremely important field. How resonances can be excited in very small structures. And that again brings us to different kinds of materials. There are different theoretical predictions, and many of the theoretical predictions we are doing today, we are unable to demonstrate because of lack of the manufacturing techniques, lack of manufacturing such small materials. So as research on machining improves, as research on micro machining improves, we would be able to manufacture very, very small components. You look at the world of nanomedicine. Okay, there is a huge application of electronics in different, for medicinal purposes, for medicine use, for health diagnosis. Okay, there are implantable antennas in the human body, antennas which are designed over the human body. Okay, antennas which radiate bidirectionally over the human body, antennas which radiate unidirectionally over the human body. Okay, so different kinds of antennas, and they are, again, just the tip of the iceberg. So we welcome new students who are excited to do research. There is a lot of things which you need to do in this branch of electronics and communication engineering, whatever subfield you choose. Okay, so I hope I have given you some idea behind this rich field of electronics. Yeah, so I would welcome any questions from you.
Request all the students to ask questions if you have any in the chat box, and we'll get it solved for you. Till then, we have got few questions through registrations. So I'll go and asking those questions. So a student asks, what is the difference between different disciplines in the electrical, like electronics, telecommunication, and all these different engineering branches in different IITs? So what is the difference between those disciplines?
Actually, there is, in that sense, not a difference between the different IITs. All the IITs will follow principally the same course material in each sub-specialization. But the difference is twofold. One, as I said to you, in some of the IITs, electronics is taught as a subfield in the mother branch of electrical engineering. But in some other IITs, like in IIT Kharagpur, electronics is taught as a different specialization, as a different discipline, okay, because of its enormity. That is number one. Secondly, a particular IIT may or may not have all specializations in electronics. For example, I told you there are typically 5 specializations in electronics. One is the VLSI, another is microwave, another is fiber optics, another is telecommunication, another is image processing. Okay, so a particular IIT may not have all specializations active. That you have to choose between by seeing which specialization you would like. But again, I would say if you are at the undergraduate level, that does not make a lot of difference, because the undergraduate curriculum is essentially going to be the same. In fact, it is pretty much the same worldwide. Okay, so so that is it. But when you go to the postgraduate level, there is where the differentiation starts. Okay, so there you must be looking at the research in a particular field, research in a particular specialization, and which area you would like to do research in, or which area you would you would like to specialize in. So there is where the differentiation starts, not so much at the undergraduate level.
So the next question we have is, what is the difference between curriculum and job opportunities in BS and BTech in EC?
Actually, this is a good question. I mean, as long as you are, both the curriculums are okay. What I feel is that as long as you are sincerely absorbing the concepts, whatever you are reading, getting a job, I don't think is a problem, particularly if you are graduating from an IIT. In general, jobs, many people get multiple jobs. I don't think getting a job is a big issue. But what might be an issue, and that is important, is that figuring out what you like. Remember, at the end of the day, you are going to spend 30 years of your career to do something. And well, though, I mean, nobody is underestimating the need for money. I mean, that is absolutely needed. But at the same time, it is also needed to follow your dreams, your ambition. So what I would say is that during the bachelor's level, as you go through the courses, try to understand yourself as to which kind of area you would like to do work in. Okay, so that is important for you to understand. So there are jobs in all the fields to varying extent. And I mean, depending on your skills, there will always be takers for you. But most important thing is that, particularly when you read a material, try to understand it. It's just not following the printed lines of the text. It is very important to understand the procedure and to really absorb the material well, so that at the end of it, you can devise or you can contemplate or you can dream of a thing of your own. So try to think of your own. That is very much needed. Okay. So as you progress through your undergraduate study, so try to have this mentality that, first of all, which area I would like to work. Ask yourself, which area pleases me? I have to do this work for a certain long time in my careers. So which area I would do? What would I do? Would I like to work in an industry? Whether I would like to work in academics, or whether I would like to do research in this particular field, or do this kind of a job. Try to understand yourself. That way you would be, you would be enriched. And again, try to think on your own. Okay, try to be a little bit more creative in your thoughts. So it doesn't come in one day. And I understand that in the undergraduate level, you would be you would have a number of subjects to read. The time is short. That is true. But even then, within that time, if you kind of absorb the subjects well, understand the subjects well, I think that is better. Okay, then I don't think job is a problem.
The next question we have is, any beginner book recommendation for us to understand the subject better?
There is no particular book. It's a vast subject. So as you go through the years, the professors who will be teaching the different courses would be telling you the relevant books. So there is nothing like, whatever, Nelson Parker in physics, or blah, blah, this book in physics. It is not like that. It is a huge area of study. So each subject will have its own books, and that is best prescribed by the professor or the faculty who would be teaching the course. So just what is important for you is to absorb the material well. Okay, so I have found, like, sincerely, I have found many students who take who kind of think, even in IITs, that do a study for 15 days, 20 days, and many of the students, what rather pains me is that there are very good students who come to IIT, but after coming, a lot of students think that the career is done for me. I would get a job anyway. Even if I get a D or a C, I would get a job anyway. Please don't have that mindset. Okay. So as I said, that please develop a liking for what you are doing. Do what you like. This is what I'm saying to you. You identify yourself. Okay. So that is very important.
The next question we have is, does the electronics branch also have computer subjects?
Yes, definitely. Definitely, they two go hand in hand, and in fact, the two subjects, all branches of engineering, they complement each other, and definitely electronics and computer science. But remember one thing: this I will again tell you, because India is doing very great in software, and we tend to go into software. We think of machine learning, artificial intelligence. They are fine. They are all fine. There is nothing wrong in them. But to think that they are the only subjects which will give me bread and butter, okay, that might not be a good way of thinking. That's why I am telling you at the very beginning, know yourself, know what you like, all people do not like computer science. So just jumping into a field for either the, like the fantasy of earning money in a short time, or for any other reason, you might think that is a shortcut to success, because so many people are getting jobs, so many people are going to in so many places. I don't think that is a proper way to think. Okay, and many of them get frustrated. Okay, so that is very important to understand your liking. I continue on all your questions. You will find that I will emphasize this idea that please do what you like. Remember this, please do what you like, because you are going to do that for 30, 40 long years of your life. And if you do not like what you do, you are not going to be successful in that field. This I can give you in writing. If you do not like what you do, you are never going to be successful in that field. Okay, if you like computer science, if you like coding, fine. But if you like hardware, so give time to yourself, relax and think what you like. That's the only way you are going to be successful and excel in your life.
So the last question we are taking, what are the fields involving overlap of quantum physics and electronics?
Yes, there's a lot of overlap. As I told you that, quantum particles or quantum electrons, even we have quantum antennas. Okay, so there is a huge overlap. There is quantum processing. So there is a lot of overlap between quantum engineering and electronics. So that you will understand as you progress to the course. Okay, so this is a very vibrant field. Okay, and I should not use the word, it is a very challenging field. If you like it, if you like new challenges, if you like to take over challenges, this is a field for you. Okay, you will meet new challenges, you will meet new design principles, you will get ample opportunities to be creative. That is very important. So that's what I'm saying. If you are like preparing for post-graduation mode, I would tell you to be more creative. But here I would tell you to try to create things. Okay, so to try to be more creative in your outlook in whatever you do. And that is one way you would understand yourself, what you like. The area in which you are more creative is the area in which you like. Okay, so that will guide you towards that direction.
All right, so I think we can conclude this session. So thank you, Professor Ghosh, for your valuable time. This session has been enlightening, and I'm sure the students have gained remarkable insights in the field of electronics and electrical. So thank you so much for joining us.
Thank you. It was a pleasure sharing my experiences with you, and I hope you would benefit from it.
Yes, thank you, sure.
Thanks.